All right, this is a test recording with the new presupposed audio filters applied, the relevant distributions of wavelengths of microphone frequency. Do a little sample reading here. A mathematical analysis of relativity theory. So I want to run through this section real quick and just kind of see if it's coherent, makes sense, because this is a huge deal. And I don't think people, obviously this isn't well talked about or related to the layman. So I want to make sure that this translates in a way that, coherently makes. So anyway, the prerequisites will be definitions and terminology. So this will be some of the lingo that's used within the mathematic framework and the theories, mathematical theories and stuff that are used for these equations, field equations. So covariant, used to describe a tensor that transforms in accordance with the rules of covariant transformation by maintaining the geometric properties or maintaining their geometric properties when transferred to a new coordinate system, defining them as independent of the coordinate system that they're being transferred to and from. Maintaining covariance is a good way to mathematically show that your theory is in alignment with the laws and postulates in which your theory is built upon, or that itself is built up upon it, which the theory itself is built upon, e.g., that the laws of physics are the same in all reference frames, right? So uh, using the theory of covariance, calculus, and differential equations, this is how they come up with things like the laws of physics are the same in all reference frames and stuff. This is how they express that. It all has to be covariant, right? The tensors that describe uh, the geometric properties of space-time. So laws of physics. So what happens to the space-time coordinate system? How it bends and warps and distorts and all that, curves, needs to be transferable to other space-time coordinate systems. And that relationship is called covariant. You can transform the tensors to a new coordinate system. They maintain their properties without needing to be corrected, anything like that. All the laws of physics will be the same in the all reference frame. Invariant, a quantity that remains unchanged under a given transformation. Something is invariant. The tensor is invariant. Actually, that doesn't just apply to tensor. Sorry. So this is the quantities that remain unchanged under given transformation. So like the speed of light is invariant, right? So that would be a constant. They apply transformations to they move it to a different coordinate system and it stays the same. Transformations. A mathematical operation that maps a set of objects to another set of objects while preserving certain properties of the original system. So, going back to how things are covariant and all that, the transformations are how you um, change from one coordinate system to another. So, you apply a transformation to the tensors, and that will allow you to change the coordinate system. So when you're talking about, like, say for example, the Lorentz transformation, that's how they got from the Newtonian framework to the relativistic framework. They do it. Let's show quick preview what a tensor is. I really should have this slide on there as well. But this is the description. This is what a tensor looks like. So, and then we'll for what that means here in a second. This should be okay. So a tensor is a mathematical object that represents a linear relationship between two sets of vectors, scalars, and other tensors. So these tensors are how the space-time geometry is defined, and this tensor specifically is how the laws of energy conservation of energy are set so that they tend to zero. Now, this is important because the space-time tensor itself describes infinite gravitational fields and infinite space-time curvature. So it doesn't satisfy the laws of conservation of energy and momentum because in a closed system, all of those things would have to tend to zero and conserved. And if that's not described in the mathematics of the theory, then it's not, covariant, then it's not in alignment with the physical phenomenon that it's trying to describe, right? So this is, if they were, this is a huge deal for them to satisfy this law and have everything being maintaining covariance, because maintaining covariance is how they they bring physicality to what they're trying to attribute to nature, right? So like without the covariance, the space-time metric system is just a bunch of jibber jabber, right? It doesn't have any physicality to it at all because it doesn't translate with the laws of physics, and it doesn't and its postulates are built upon saying that all the laws of physics are the same in all reference frames. Well, without these without the tensor satisfying the laws of conservation of energy and momentum, that wouldn't be true. So this is a huge deal. So they have to implement this thing called a pseudo tensor, which we'll get into, which we'll move on to now. So remember, the first tensor is just basically a coordinate is just how you can define a coordinate system to express a linear relationship between two objects within the coordinate system. I think that's a pretty fair description. And then from that, there are these things called pseudotensors that should be above the first order. Okay. Okay, so from that, there are these things called pseudotensors. Now, pseudotensors act like a tensor under some transformations, but not others. So they're they they can be used as kind of like a placeholder in under certain transformations, um, and that will satisfy the laws of conservation of energy and momentum. However, the use of the pseudo tensor itself breaks covariance because the pseudo tensor, when contracted, is revealed to be a first order intrinsic invariant differential. What that means is that's a type of invariant tensor that's coordinate dependent and changes under transformations. It is composed solely of the components of the tensor and its first derivatives. It is not derived from the field equations themselves and cannot be obtained from second order field equations equations, which violates the mathematical structure that relativity theory is based on, or is based upon. Since it's based upon the theory of covariance, um, and that the laws of physics should be independent of the choice of coordinate system. So invoking this to satisfy it actually destroys catastrophically destroys the relationship that that would be in alignment with uh with covariance, right? To satisfy the postulates of which the theory is built upon, and then like using this to mathematically describe it. This this interjection of a pseudotensor to satisfy a law of physics that the field equations don't naturally satisfy because they describe infinity, and infinite curvature and infinite gravitational fields. So interjecting this ad hoc actually destroys it fundamentally. So when they say, "Oh, well, these equations reduce back to Newton's equations," and things of that nature, they actually don't at all because of this. Um, so we'll go into what contraction means because that's how you can analyze what's going on with the tensor basically, and you can determine if it's part of the if it's derived from the field equations or if it's derived from a pseudo tensor that was derived from the field equations. And if that's the case, then you got yourself a first order intrinsic invariant differential, which doesn't exist within the system, and it's just kind of like an ad hoc explanation. Okay, so contraction, a mathematical operation that involves summing over the components of a tensor in a specific way to extract information about the state of the tensor it's describing. So they're of the state of the system the tensor is describing. So yeah, so you can basically apply different restrictions to the tensor, different stresses to it. You could say to to make to do mathematical analysis of it to make determinations about what it's saying about the system, and is it truly in alignment, and is it truly covariant under certain circumstances, right? So you could think about it like, say you're baking a cake, and a layered cake, and it's a four layered cake, and if you were to compress the cake down into a single layer, let's say every layer is vanilla. So when you compress it down to one layer, the whole thing is a vanilla cake, and you're like, okay, good. I definitely all the ingredients that I use to make this vanilla cake are indeed um, reduced back to the vanilla ingredients, right? So everything's on the up and up. It's a vanilla cake, right? So let's say you did the same thing, and when you got the final layer cake compressed down, it was revealed that you had a chocolate cake. And what does that mean? Well, it means some of the ingredients you put in there aren't aren't related to the vanilla cake. So you don't, in fact, while it appears like you have a vanilla cake, when you contract it and analyze it, so to speak, you find out that it's not a vanilla cake. So that's basically what that means, in terms of contraction on a pseudotensor and summing up the indices, um, to impose certain restrictions on it to find out things about how the how the tensor is describing the system. Conservation of energy and momentum. A physical principle that states that the total energy and momentum in a closed system are conserved over time. What that means is energy can't be created or destroyed. Everything has to be conserved. So these infinite gravitational fields and infinite space-time curvature things um, don't exist in nature, and they're a result of the coordinate system used to describe nature, and um, these are laws that need to be satisfied within that coordinate system if the coordinate system is to be attributed to have a to be physically meaningful to the equations that it describes, right? So like is it so when it says that space-time curvature is bending that much, even though space-time curvature is a coordinate system, it's a concept. um there actually has to be something out there that's curving, due to the presence of matter and energy, right? um, and that's basically uh, a law that has to be satisfied if you're going to make that connection, right? If you're going to attribute physicality to the equations and make them physically meaningful. So, and then a second order differential equation. A second order differential equation is a mathematical equation that involves a function, its derivatives, and its second derivatives. Einstein's field equations are second order differential equations that describe the relationship between spacetime curvature and the distribution of matter and energy within it. The curvature of spacetime is affected by the presence of matter and energy, and the field equations provide a framework for understanding this relationship. So basically, this creates the framework in which, um, you can that the quote unquote solutions that are derived from these field equations, right? This describes how to interpret those solutions, how those solutions have to be in alignment with a certain framework, um, how it has to be covariant and all that, right? Now, keep in mind the use of the pseudo tensor, which all these solutions are derived from, like such as the Schwarzschild radius, the Schwarzschild metric, the Kerr metric, all these metrics that are used to describe black holes, anything like that, expansion, contraction of space time, anything that uses the pseudo tensor, which is pretty much every metric, or every solution, is kind of is not kind of it's poisoned by um, the fact that it's derived from a pseudo tensor that is a first order intrinsic invariant differential, which doesn't exist in the system. So it's just revealed as like a ad hoc hot fix to the situation.